Conjugation occurs whenever p orbitals can overlap on three or more adjacent atoms. Take, for example, having a p orbital next to a double bond. If the p orbital is in the allylic position to the double bond, it is considered to be in conjugation with that double bond. Now, if we take and combine four p orbitals on adjacent atoms, we can make something called a 1,3 diene. The 1,3 diene is a conjugated system. We have two double bonds. The first double bond occurs on carbon 1, the second occurs on carbon 3, and now we have four p orbitals that can delocalize electron density over those four carbon atoms. Delocalization. Delocalization is having three or more p orbitals on adjacent atoms, which allows the p orbitals to overlap and electrons to delocalize. If you think about it this way, delocalization is a way to stabilize electron density by distributing that electron density over more carbon atoms. Take, for example, a 1,3 butadiene. The electron density is stabilized over the four carbons as compared to two isolated double bonds. This allows the system to be more stable and lower in energy than we would typically see. We can have dienes of two types. We can have isolated dienes, such as 1,4-pentadiene. It's isolated. That means that the pi bonds in the 1,4-pentadiene are too far apart to be conjugated and are isolated from each other by an sp3 carbon atom. The isolation that occurs in 1,4-pentadiene does not allow this compound to be lower in energy than 1,3-pentadiene. The 1,3-pentadiene would be a conjugated diene because from carbon 1 to carbon 4, all the p orbitals are connected. Where with 1,4-pentadiene, the double bonds are located on carbon 1 and 2, and in 4 and 5. The sp3 carbon in between the two double bonds on 1,4-pentadiene do not allow delocalization to occur. So as we look at conjugation, the easiest system to deal with is the conjugation of allylic cations. If we take a double bond and on the adjacent carbon put an sp2 hybridized carbon with an empty p orbital, we have an allylic carbocation. That allylic carbocation can undergo delocalization. I can take the electron density between carbon 1 and 2 on the left and give that to carbon 2 and 3 to satisfy the lack of electron density in the carbocation. Doing so rotates my picture 180 degrees and shows now the carbocation is on carbon 1. This conjugation that we have with an allylic cation and the ability to undergo delocalization allows us to lower the energy of that carbocation. So allylic carbocations are going to be lower in energy than isolated carbocations. So let's take a look at this delocalization. We can draw resonance structures for an allylic carbocation. Here on the left, carbon 1 and 2 have a double bond, and carbon 3 has a carbocation. Well, if I take the electron density between carbon 1 and carbon 2 and migrate that to between carbon 2 and 3, I now have a carbocation on carbon 1 and my electron density for my double bond between carbon 2 and 3. This delocalization means if I draw a hybridized structure, I have electron density shared between carbons 1, 2, and 3, and carbons 1 and 3 have a partial positive charge. The true allylic carbocation is a hybrid of the two resonance forms. Okay, the positive charge is delocalized over the two terminal carbons, and that delocalization forces of the charge, the delocalizing the charge stabilizes the allylic carbocation, making it more stable than a primary carbocation. So if we look at the stability of allylic carbocations, you might recall that a methyl carbocation is the least stable of the carbocations we've talked about. A primary is slightly more stable, but less stable than a secondary carbocation. The tertiary carbocation is the most stable. The allylic carbocation is about the same stability as a secondary carbocation. Now, if we look at an allylic carbocation, it looks like it's a primary carbocation, but that double bond to the left of the carbocation, as pictured, allows it to be the same stability as a secondary carbocation. If we look at electrostatic potential maps for a localized and delocalized carbocation, the localized carbocation is electron deficient, the blue region, on the primary carbocation. And that blue region, that electron deficiency, is only on the carbon that has the positive charge. If we look at the electrostatic potential for the allylic carbocation, we'll see that the blue region is mitigated. It is less electron deficient, and it is now localized over two terminal carbons. Therefore, our system is more stable having an allylic carbocation than a primary carbocation. So, how can we tell if we have an allylic carbocation? Well, the first thing we want to do is figure out what chemical shifts are possible with a carbocation. So if we think about a carbon-13, what we're going to see here is a this is actually a tertiary carbocation, is very deshielded. It shows up at 330 ppm, which is even further than we typically see on a carbon-13 NMR. Remember, we only go to about 220 ppm on the carbon-13. The allylic carbocation, because you have delocalization of charge, is now going to be less deshielded. And it's the two carbocations in this example will show up at about 224 ppm.